Hello, everyone. Tonight we're going to step away from the noise of the day and drift into one of the oldest, most beautiful questions ever whispered into the dark. We'll be tiptoeing into a mystery that feels as old as time itself, and yet paradoxically asks about a time before time. Tonight, we're going to explore the quietest of all concepts, nothing. And I mean truly nothing. No light, no sound, no space, no time, no you, and no me. We're going on a journey to a place so profoundly empty, it makes a blank page look cluttered. But don't worry. You probably won't survive this journey in any conventional sense. It's a voyage for the mind, not the body. A deep dive into an ocean of quiet that can't actually drown you. Now, before you go and watch, please take a moment to like and subscribe to this video, but only if you truly enjoy what I do. And if you're a night owl with me, feel free to let me know in the comments where in the world you're watching from and what time it is for you. I always love to see the global hum of sleepy thinkers. Now let's begin our descent. Take a slow, deep breath with me. Not to fill your lungs with any great cosmic insight just yet, but simply because we're about to dive into a concept that seems so simple, but is slipperier than a bar of soap in a black hole. Tonight's question is, what do we really mean by nothing? You'd think that of all the things in the universe or outside of it, nothing would be the easiest to explain. After all, it's, well, nothing. No things, no stuff, just emptiness, right? But here's where it gets interesting. The more carefully we examine nothing, the more it starts to look suspiciously like something. And as we'll see in both science and philosophy, nothing can wear quite a few disguises. In fact, there are several kinds of nothing, each one stranger and more counterintuitive than the last. Let's start small with something familiar. Something you can almost reach out and touch right now. Picture an empty jar. Maybe it's a jar that once held your favorite peanut butter, or perhaps it's a pristine glass jar fresh from a new home goods store. You unscrew the lid and peer inside. It appears empty. There's no peanut butter, no sugar cubes, not even a single grain of rice clinging to the bottom. Most people, if you asked them, would call that nothing. But of course, as you know, that's not quite right. The jar is full of air. And what is air? It's oxygen. Nitrogen? A bit of carbon dioxide, maybe the lingering scent of cinnamon from whatever it held last week. Molecules are bouncing around in there like invisible popcorn. If you were an ant with a chemistry degree, you'd be overwhelmed by just how not nothing it really is. This is a very simple and, in a way, very profound truth. Our perception of nothing is always relative. It's an absence of what we expect to find, not an absence of everything. You're not saying the jar contains nothing. You're saying it contains no peanut butter, which is a very different thing indeed. We carry this habit of mind with us into our deepest questions. We talk about the void, or the emptiness of space, but we are always subtly projecting something onto it. A historical fact you might find interesting is that in ancient Greece, many philosophers, including the great Aristotle, were deeply uncomfortable with the idea of a void. They believed that nature abhors a vacuum and that the cosmos must be a plenum, a continuous filled whole. This idea held sway for over 1,000 years, influencing how people thought about the cosmos. It was only much later during the scientific revolution that thinkers began to seriously consider the possibility of empty space, and even then, they filled it with things like ether to help light waves propagate. The human mind is very reluctant to let go of the idea of a medium, of a container, of a something that allows for things to happen. So let's step it up a notch. What if we could suck all the air out of that jar? What if we vacuum sealed it until there was no atmosphere left inside at all? Now we've got a vacuum, or what we might call empty space. Is that nothing? Well, we're getting closer. But even this vacuum isn't truly empty. First, there are still fields inside. Not cornfields, but the invisible kind that exist everywhere in the universe. These are quantum fields, and according to modern physics, they can never be completely turned off. Even in their lowest energy state, they still ripple with possibility. This is where things start to get quantum weird, and in a very quiet way. In the early 20th century, scientists like Max Planck and Werner Heisenberg discovered that the tiniest levels of nature are never truly still. Even a perfect vacuum devoid of matter and energy is still humming with uncertainty. Tiny particles pop into and out of existence constantly. They're called virtual particles, and they're part of what physicists call quantum fluctuations. In other words, even nothing is always doing something. This is a crucial concept, a subtle little detail that changes everything. It's like discovering that even the deepest part of the ocean, the parts we thought were perfectly dark and silent, are teeming with invisible life, with creatures that shimmer and glow only when you're not looking. We're talking about a kind of nothing that's not a dead end, but a restless buzzing sea of potential. It's a fundamental part of the universe's fabric, a baseline hum of existence that can't be switched off. It makes you wonder if nothing is always doing something. Then does nothing, as a concept, even exist at all? Or is it just a useful word we invented to describe a state of very low something? Think about your empty jar again. If we could make it truly vacuum sealed, removing every molecule of air, and then shrank ourselves down to the quantum scale, we'd still see things happening. Not because matter is leaking in, but because the fabric of the universe itself is restless. It fizzes with energy. The vacuum is like a quiet ocean that looks calm from above but teems with life below the surface. This is a point of great debate among physicists and philosophers. Some argue that because these virtual particles exist for such fleeting moments, they don't count as real in the same way that a proton or an electron does. They borrow their existence from the quantum uncertainty principle, and they must disappear before they can be directly measured. So in this view, the vacuum is still empty of stable matter. But others argue that even a fleeting existence is still an existence. A flash of lightning in a storm lasts only a second, but it is still a real event. A fleeting thought is still a thought. And this is a very interesting little debate. Is a universe full of fleeting virtual particles? A universe full of something or nothing? A fact that is not widely known outside of physics circles is that this jittery nature of the vacuum, this quantum foam, has real measurable effects. It can subtly shift the energy levels of electrons in atoms, a phenomenon called the Lamb shift. It can also cause a very faint, measurable force between two uncharged metal plates, placed incredibly close together, known as the Casimir effect. This is what's so beautiful about science. What was once a wild speculative idea that the vacuum is not empty can be tested in a lab, no matter how counterintuitive it seems. A good joke for the road. What did the physicists say when they discovered the Casimir effect? Looks like my two metal plates are attracting each other for absolutely no reason at all. It's a very subtle joke, I know, but you'll get it after some rest. So here we are, two versions of nothing down, and neither one is truly empty. We have the mundane nothing of an empty jar which is just filled with air. And we have the quantum nothing of a vacuum which is still filled with fields and particles that flicker in and out of existence. But let's take it even further. Let's go to the edge of what we can even imagine. What if we removed space itself? Not just the stuff in space, but space itself. Gone. No dimensions, no up or down, no left, no right. Can we even imagine that this is where language starts to fail us? Without space, we can't describe where anything is, or even where nothing could be. It's not a black void. It's not a white screen. It's not darkness, silence, or emptiness. It's the absence of place itself. You can't put your mind inside it, because there's no inside. We've evolved to think in terms of spatial relationships, to navigate our world, to find our keys and our friends. So when we try to picture a complete absence of space, our brains seize up like a cosmic computer with a fatal error. And if you think that's complicated, let's get even more radical. What if we took away time as well? No seconds ticking by, no change, no motion. A timeless, spaceless, matterless. What some physicists and philosophers propose that this is the only true form of nothing. The absolute absence of everything, including the dimensions in which things can exist or happen. But now we're dealing with something almost paradoxical. If there's no space or time, can we even say it exists? And if it doesn't exist, then what is it? A final gentle joke for this part of our journey. What did the timeless, spaceless, matterless realities say to the Big Bang? It's about time something happened. It's a bit like trying to draw a square circle. The words make sense individually, but together they become nonsense. In the same way, our brains, which evolved to track fruit faces and predator footprints, aren't naturally equipped to visualize the absence of all things. Nothing in its most extreme definition might be not just beyond our senses, but beyond thought itself. Of course, some philosophers have argued that nothing doesn't make sense at all, that it's a concept invented by language. When we say something is not there, like when your friend says, "There's nothing in the fridge," we still mean something. We mean the fridge is present, just empty of the items we want. But when we talk about absolute nothingness, we're using words that point to an absence we've never encountered. The German philosopher Martin Heidegger famously asked, "Why is there something rather than nothing?" It's one of those questions that sounds obvious at first, but grows more unsettling the longer you think about it. And the more we learn from science, the more it seems that nothing might not just be hard to find, it might not exist at all. So where does that leave us? It leaves us with several kinds of nothing, all of which are actually quite something. From airless jars to seething quantum vacuums to theoretical voids outside of space and time, nothing is not one neat concept. It's a spectrum of increasingly abstract possibilities, and in the end, we might have to accept that pure, total nothingness may not be part of reality at all, only part of our imagination. But that doesn't mean the question is pointless. Quite the opposite. Asking what nothing is helps us understand what something really means. It's in the contrast that clarity emerges, or at least a kind of peaceful confusion. And as we'll see when we explore the origin of the universe, nothing may be not the end of the line, but the beginning of a very strange road. Hello again, and welcome back to our quiet little journey. We left off staring into the heart of nothing, only to find that it was far from empty. We peeled back the layers of a seemingly vacant jar, then a perfect vacuum, and each time we discovered a restless humming. Something underneath. Now we're going to dive deeper into that humming. We're going to go to the very edge of our understanding of what it means to be and peer into the quantum vacuum. And as you get comfortable, maybe sinking a little deeper into your chair or your bed, take a moment to imagine a single solitary cubic centimeter of space so empty that we've pulled out every single particle, every last photon of light, every stray atom. You might picture it as the blackest black, a perfect absolute void, a place of total stillness. But the truth is, this is a very active, very noisy place. It's a place where things are not just allowed to happen, they must happen. This idea began to take shape in the early 20th century as physicists grappled with the strange new world of quantum mechanics. It was a world that didn't play by the rules we were used to. In our everyday experience, a bowling ball at rest on the floor is just that, at rest. It's not randomly deciding to float a few inches off the ground for a millisecond, or suddenly morphing into two smaller bowling balls before vanishing again. But in the microscopic world of atoms and particles, things are much more chaotic. The physicist Werner Heisenberg gave us the uncertainty principle, a cornerstone of quantum mechanics, which tells us that we can never know both a particle's exact position and its exact momentum at the same time. The more precisely we know one, the less precisely we know the other. This isn't a problem with our measuring instruments. It's a fundamental built-in feature of reality. And this principle has a profound, almost poetic implication for our empty vacuum. Because of the uncertainty principle, even a perfect vacuum can never have a precise, unchanging energy of zero. If it did, we would know both its energy zero and its duration forever with perfect certainty, which the principle forbids. Instead, the energy of a vacuum must fluctuate. It must have a tiny restless energy, constantly shifting and changing. Think of it like a perfectly calm ocean. From a distance, it looks flat and motionless. But up close, if you get down to the surface, you see that it's actually made of countless tiny ripples and waves all moving and interacting. The quantum vacuum is like that ocean, but instead of water, the ripples are quantum fields. And what are these ripples? They are the spontaneous appearance and disappearance of what we call virtual particles. These particles borrow their energy from the vacuum for a brief, fleeting moment, and then they must vanish again to pay back the cosmic loan. It's like a cosmic, very quiet pop-up market. A particle-antiparticle pair, like an electron and a positron, can pop into existence, exist for an unimaginably tiny fraction of a second, and then annihilate each other and vanish, leaving nothing but the vacuum behind. A little-known fact is that these virtual particles are not just a theoretical oddity. They are what give rise to the lampshift we talked about before, and they are also the reason that certain atoms have slightly different energy levels than we would expect them to have otherwise. The buzzing of the vacuum, as it were, is what makes the universe a little bit different than a purely classical, predictable place. Imagine for a moment that you are a silent observer, a tiny, undetectable consciousness floating in this perfect quantum vacuum. There's no light, so you can't see anything. There's no sound, so you can't hear anything. But if you could somehow sense the energy around you, you would feel a constant, gentle sizzle, a fizzing. You would see what looks like nothing but. You would sense the ceaseless silent creation and annihilation of countless pairs of particles. It's not a dramatic show, not a fireworks display. It's more like a subtle shimmer, a deep underlying vibration of reality. In a way, the vacuum is not empty. It's full of potential. It's an ocean of possibilities waiting for a reason to become real. This is why some physicists have argued that the universe itself in all its majestic glory, with all its galaxies and stars and people and planets, could have arisen from a fluctuation in this quantum vacuum. A great cosmic pop that didn't come from nothing but from a potential-filled nothing. This is not a popular belief, but a theoretical one. It's one of those ideas that is so mind-bendingly quiet and powerful that it's easy to miss. The thought is that a massive universe-sized fluctuation could have occurred, a bubble in this quantum foam that expanded and cooled to become the universe we see today. The humor in this is that the entire universe may be, in a sense, a fleeting mistake that just happened to last a very, very long time. This isn't just about particles. This is about the very nature of reality. The historical fact here is that this idea of the quantum vacuum as a zero-point energy field wasn't just a sudden revelation. It was the culmination of decades of thinking about the strange behavior of light and matter at the smallest scales. It started with Max Planck's work on blackbody radiation, which suggested that energy could only be emitted in discrete packets, or quanta. Then Einstein used this idea to explain the photoelectric effect. Then came the work of Heisenberg and others, and gradually, bit by bit, the classical view of a predictable deterministic universe gave way to the quantum one, where probabilities and possibilities reign supreme. The quantum vacuum, with its jittery, uncertain energy, is the ground floor of all this strangeness. It's the ultimate example of something that seems simple, but reveals a deep underlying complexity the closer you look. The physicists' debate over whether a quantum vacuum is truly nothing is a fun one. Some say it's still a form of something because it has properties like a certain energy density and can exert forces. Others say it's the truest form of nothing that can exist within our physical universe because it's a state of being devoid of actual stable particles. The discussion is a bit like arguing whether a single drop of water on a hot skillet is a puddle, or just a temporary state of being a drop. It's a matter of definition, but the definitions here are as vast as the cosmos. So where are you now in your mind's eye? Are you still in that little cubic centimeter of silent space? Can you feel the faint energetic shimmer? It's not scary, is it? It's not a void that wants to swallow you whole. It's a gentle humming emptiness that contains all the potential for everything. It's a quiet testament to the idea that the universe, even at its most fundamental level, is not a static thing. It's a process. It's a verb, not a noun. And this idea of an active, restless vacuum is what allows us to even begin to talk about how the universe could have come into existence without a pre-existing something to come from. We don't need a magical starting point. We have a starting state that is already rich with potential. It's the ultimate what if. What if a tiny ripple in the fabric of nothing became so big it became everything? And what is the point of all this? The point is not to fill your head with facts to be memorized, but to invite you to change the way you think about emptiness. When you look at an empty space at the darkness of the night sky, you are not looking at a place where things are not. You are looking at a place where things are humming, waiting, rippling with possibilities you can't see with your eyes. The emptiness is not a dead end. It's the beginning of a conversation, a whispered promise of what might be. It makes you feel a little less alone, doesn't it? Knowing that even in the quietest, most seemingly desolate corners of the universe, there's a gentle, energetic buzz, a constant, cosmic murmur of creation and annihilation. It's a lullaby sung in a language of particles, a poem written in the language of physics. And as we continue our journey, we'll see how this quiet hum might have grown into the roar of the Big Bang, a sound so loud it has resonated for billions of years, and a story that is still being told. So close your eyes and listen to the stillness. It's not nothing. It's the universe waiting for its next word. Just remember as we drift that the most profound insights are often found in the places we least expect them. In the quiet, in the still, in the emptiness. It's a nice place to be, isn't it? A safe place? A place that's always full of possibilities. And with that, let's rest for a moment and prepare to move on to a much louder chapter in our story. And now, with our minds humming with the quiet energy of the quantum vacuum, let's take a gentle leap forward, or perhaps backward depending on how you think about time. We're going to take a calm stroll through the history of, well, everything. But don't worry, you won't need a time machine or a seatbelt. Just a quiet mind, a comfortable pillow, and perhaps a sense of cosmic wonder. Tonight we're visiting the moment the universe began, or at least the moment our current understanding says it did. This is the story of the Big Bang. Not a loud explosion in space, despite the dramatic name, but a gentle unraveling of space itself. A moment so strange that it gave birth to not only everything we see, but the very space and time in which we see it. And to start, let's disarm one of the biggest misconceptions we have about it: the name. The term Big Bang was actually coined as a joke. Back in the 1940s, a brilliant but skeptical British astronomer named Fred Hoyle used the phrase during a BBC radio broadcast. Hoyle didn't believe in the idea of a universe with a beginning. He was a champion of the rival theory at the time, the steady-state model, which suggested that the universe had always existed. So when Hoyle sarcastically referred to the competing idea as the Big Bang, he meant it as a jab, a flippant nickname for what he thought was a silly, unscientific concept. The name ironically stuck. The theory did too. And poor Fred Hoyle became eternally linked to a theory he didn't believe in, all because of a throwaway line on the radio. But let's be clear. Despite the name, there was no bang. At least not in the way we usually think of one. An explosion in the everyday sense happens in space. A firework goes off in the sky, sending sparks outward through the air. A volcano erupts, hurling ash and lava across the land. These are loud, violent events that happen at a specific location, with debris flying outward into a larger background. But the Big Bang was not like that. The Big Bang wasn't an explosion in space. It was an expansion of space. That difference might seem subtle, but it's everything. Imagine blowing up a balloon. You take a red marker and draw little dots all over its surface. These dots represent galaxies. As you inflate the balloon, you'll notice that the dots move away from each other. Not because they're crawling across the rubber they're fixed in place, but because the surface itself is stretching. Every bit of balloon is getting bigger, and that's carrying the dots apart. That's what the universe is doing. Galaxies aren't flying apart through some vast emptiness. Space itself is expanding. The distances between galaxies grow because the fabric of the cosmos is stretching. The balloon gets bigger, so everything on it gets farther apart. And here's the key part. The balloon doesn't have a center. Every point is moving away from every other point. There's no central explosion site. If you were standing on any one of those dots, it looks like you're at the center with everything else rushing away. But that's just an illusion caused by uniform expansion. Our universe works in the same way. No matter where you are, you'll see galaxies receding in all directions. It gives the impression that you're at the center of the bang, but so does every other galaxy. There is no center. There is no edge. Just a boundless stretching space-time. Now let's gently rewind the balloon. If we shrink it back in time, the dots get closer together. The surface contracts. The balloon tightens down until at some finite point in the past, it reaches a state of unimaginable density and temperature. A kind of cosmic seed, a singularity, as it's sometimes called. Not a thing inside space, but the point at which space itself began. This is what we call the Big Bang. It wasn't a sudden firework in space. There was no pre-existing vacuum, no cosmic firework lighting up a black sky. Instead, it was the sudden dramatic expansion of space itself, the birth of time energy and the laws of physics as we know them. And no matter where you stand in the universe, it looks like everything is expanding away from you. Not because you're special, but because space itself is growing in all directions. A fun fact: you may not know, the idea of an expanding universe wasn't immediately accepted. One of the great academic debates of the early 20th century was between those who supported the static universe model, a cosmos that was fixed and unchanging, and those who saw the evidence for expansion. The evidence for this expansion is what really put the Big Bang on the map. In the 1920s, an American astronomer named Edwin Hubble was peering through his telescope at distant galaxies. He noticed something very strange about their light. It was redshifted. Think of the Doppler effect. When a siren on an ambulance speeds toward you, its pitch sounds higher. As it moves away, its pitch drops. The same thing happens with light waves. When a star or a galaxy is moving away from us, its light waves get stretched out, shifting them toward the red end of the spectrum. When Hubble observed the redshift of distant galaxies, he realized they were all rushing away from us. The farther away they were, the faster they seemed to be moving. It was a cosmic clue, a whisper from the past, telling us that space itself was stretching and carrying everything along with it, like raisins in a rising loaf of bread. And this leads us to one of the most mind-bending questions of all: what about time? If the Big Bang was the beginning of space, was it also the beginning of time? Our human minds are so deeply conditioned to think in terms of linear cause and effect. Before breakfast, there was sleep. Before sleep, there was brushing your teeth. Before that, probably some late-night snack you're not proud of. We always assume that everything has a before. So when someone says time had a beginning, it's tempting to ask, yes, but what was before that? And that's where the gently absurd analogy comes in again. Asking what happened before time began is like asking what's north of the North Pole. The North Pole is the top of the world. It's not just a very cold place with polar bears and the occasional elf workshop. It's the furthest north you can go. Try walking north from there, and you'll just start heading south. In the same way, time reaches a kind of boundary at the Big Bang. It's not that something was hiding behind it. It's just that the concept of before loses its meaning. In fact, many physicists describe the Big Bang not as a moment in time, but as the moment when time itself became meaningful. Before that, if we can even say before, there may have been no flow of time at all. Just a timeless, spaceless state outside the bounds of our physics. It's a bit like asking what your phone battery was doing before it was manufactured. It didn't exist yet. There was no function, no capacity, no timekeeping. Only after the phone is assembled, charged, and powered on can it start ticking and notifying you about emails you'll probably ignore. Similarly, the universe may have been unpowered, so to speak, until the Big Bang flipped the switch. And with that flip came time-space energy and all the cosmic ingredients that followed. Of course, this raises a different kind of question, one that is still very much an open academic debate. If time began at the Big Bang, what caused the Big Bang? Doesn't a cause require time to precede an effect? This is one of the slipperiest concepts in all of physics. Most cause and effect relationships we know depend on time flowing forward. You toss a ball, then it flies. You pour tea, then it fills the cup. But if the universe began in a timeless state, the normal rules don't seem to apply. Some physicists speculate that the cause of the Big Bang may not be a cause in time, but a kind of boundary condition, a set of starting rules that simply are like a board game that springs into being with the dice already in motion. There is no first player because the rules themselves begin the game. But this idea isn't the only one out there, and we'll be exploring other possibilities in our quiet journey. What's beautiful about this idea is that it doesn't require a creator or a spark from outside the system. It simply states that the system itself, the universe, came into being with its own rules. And the question of what happened before is a bit of a cosmic joke on us. It's a question our language is designed to ask, but one the universe isn't designed to answer. So let's leave our minds floating in this moment of supreme strangeness. The universe as a balloon. Time as a curved surface with no beginning. The Big Bang not a noisy explosion, but a quiet, powerful unfolding of everything. A beginning not in fire but in form. Not in a bang, but in a breath. The breath of space itself. And in this strange new way of thinking, we find that the mystery of nothing isn't what came before it, but how we ever thought there could have been a before at all. We are part of a story that, according to our best understanding, didn't start at a moment in time, but started time itself. And that's a humbling, mind-bending, and strangely peaceful thought. It's the kind of thought that can make your pillow feel a little more comfortable and the night sky a little more profound. We've now entered a quiet, beautiful, and profoundly strange place, a universe that began not with a bang, but with a breath. And that breath was in fact incredibly fast. So fast it feels like a cosmic whisper. We're talking about cosmic inflation, a silent boom that may have laid the groundwork for the Big Bang as we know it. It's one of the most astonishing concepts in modern cosmology, and it helps answer some puzzling questions about the universe's shape, temperature, and structure. But it also opens up some new ones, including what made the universe inflate in the first place and what was there before that. To explore this, let's start with a curious observation, one that puzzled cosmologists for decades. When we look out into the night sky with our most sensitive instruments, we see that the universe is remarkably uniform. The temperature of the cosmic microwave background, CMB, the ancient light from the early universe, is nearly the same in every direction. We're talking about differences of less than 1 part in 100,000. That's an astonishing level of smoothness. But here's the riddle, which is known as the horizon problem. Regions of space that are currently so far apart that they could never have interacted even at the speed of light somehow ended up with nearly identical properties. It's like baking two loaves of bread on opposite sides of the solar system and finding out they rose at exactly the same rate, with the same number of air bubbles and the same golden crust. How did they know to behave the same way? This was a major point of academic debate. There's also the flatness problem. The observation that the universe appears to be geometrically flat, which means parallel lines stay parallel over vast distances. For this to be the case, the early universe would have needed to be balanced with extraordinary precision between expansion and gravity. Even the tiniest deviation in density would have led to a very different cosmos, either rapidly collapsing back in on itself or expanding too quickly for galaxies to form. And finally, there's the monopole problem. Not the board game, but the prediction from early physics theories that heavy magnetic monopoles, hypothetical particles with only a north or south pole, should have been produced in abundance during the high-energy early universe. Yet, we've never found a single one. These problems seemed like clues, hints that something important was missing from our understanding of the universe's earliest moments. Enter inflation. In the early 1980s, a physicist named Alan Guth proposed a radical idea. What if just after the birth of the universe, perhaps even at the very moment of its emergence, space underwent a brief period of exponential expansion, not just growing steadily, but doubling in size again and again faster than the speed of light for a tiny fraction of a second? This is the theory of cosmic inflation, and it changed everything. According to inflation, the universe expanded by an incredible factor, perhaps by 100 trillion times in less than a trillionth of a second. That's not just fast, that's almost unimaginably fast. But because it happened so early and ended so quickly, it didn't break any physical laws. In fact, Einstein's theory of relativity allows space itself to expand faster than light. It's only objects within space that are bound by that speed limit. So, what does inflation do for us? Well, it solves the horizon problem neatly. If all the matter and energy in the universe were originally packed into a tiny region, so small that it could come into thermal equilibrium, then inflation would have taken that tiny uniform patch and blown it up to cosmic size. That's why we see such smoothness across vast regions of space today. They were once close enough to communicate. Inflation also flattens space like pulling on the corners of a crumpled sheet. The more you stretch it, the flatter it appears. Just as a balloon, when inflated enough, starts to look like a flat surface to an ant walking on it, the universe becomes increasingly flat as it inflates. So, the flatness problem is solved too. And what about those pesky magnetic monopoles? Well, if they were produced before inflation, they would have been diluted to near nothingness during the rapid expansion spread so thin that they'd be almost impossible to find. Problem solved once again. Inflation then acts like a kind of cosmic prequel. It happens just before the hot, dense universe we associate with the Big Bang. You might even think of the traditional Big Bang as the after-party, the moment when inflation ends, and all the energy stored in the inflating field is released in a burst of heat and light. This is called reheating. And it's the point when the universe becomes filled with particles and radiation, setting the stage for stars, galaxies, and everything else. So what sparked this period of rapid expansion? The short answer is we're not entirely sure, but we have some compelling ideas. Inflation is thought to have been driven by a kind of field similar in concept to the fields we discussed earlier in quantum theory. This hypothetical field is called the inflaton field, and like other fields in physics, it has an energy associated with it. Imagine the inflaton field as a ball sitting on a hill. While it rests near the top, its energy remains nearly constant enough to drive the exponential expansion of space. But eventually, the ball rolls down the hill. As it does, inflation ends, and the stored energy of the field is converted into particles and radiation. The universe becomes hot. Time begins to tick in the way we understand. And what we usually call the Big Bang gets underway. It's a beautiful idea, one that turns a chaotic birth into a graceful unfolding. But as always, it raises more questions. For example, what existed before inflation? Was there a pre-inflationary state, a vacuum, a quantum fluctuation? Was inflation itself eternal spawning, countless bubble universes in an endless cosmic froth? A little-known fact is that this is one of the more fiercely debated areas of modern cosmology. The idea of what came before inflation is just as perplexing as what came before the Big Bang itself. In a fun twist, it even has a name, the initial singularity problem for inflation. The debate over whether inflation itself had a beginning, or whether it is an eternal process creating new universes endlessly, is still very much an open question. Some models suggest exactly that a process called eternal inflation, where inflation never really ends but continues in other regions, creating an infinite multiverse of pocket universes. Each bubble could have its own physical constants, its own dimensions, even its own concept of time. Our universe just happens to be one that slowed down enough to allow stars, planets, and sleepy scientists to emerge. It's a beautiful idea, one that brings a gentle sense of peace. The universe, in all its vastness, didn't just burst into being from nothing. It inflated into potential a silent boom that left us with the space to exist. It's the ultimate cosmic magic trick, but one based on math, not sleight of hand. The joke here is that the universe may have started with a silent, invisible flash of genius that no one could see. A cosmic sneeze that created everything, but no one was there to say, "Bless you." And we're still cleaning up the mess billions of years later. Observations of the cosmic microwave background, the faint glow from the early universe, are helping us search for clues. Tiny fluctuations in that glow, which inflation predicts, have already been seen. They're like fingerprints left behind by the earliest moments of cosmic expansion, and maybe we'll find more evidence that inflation happened, or even hints about what came before. For now, cosmic inflation remains one of the most elegant, powerful, and mind-expanding ideas in science, a moment of near-infinite speed and silence in which the universe didn't explode into being, but inflated into potential. Not a bang, not a flash, but a breath, deep, fast, and utterly transformative. With the silent, lightning-fast expansion of inflation now settled in our minds, let's take another slow breath and consider a different path. A path that doesn't lead to an initial bang or a fleeting whisper, but to a continuous cosmic dance. We're stepping into the idea of a universe with no true beginning, just a cyclical rhythm, a slow cyclical breath expanding outward, contracting inward, and expanding again. Inhale, exhale, over and over. This calm and curious rhythm lies at the heart of a theory that challenges one of our most cherished assumptions about the universe, that it began from nothing. This idea, gently provocative and deeply elegant, is known as the Big Bounce, a model where the universe didn't explode out of a singularity, but rebounded from a previous state, a cosmic do-over. And at its core is a field of study called loop quantum cosmology. Now let's ease into the concept. In the standard Big Bang model, the universe begins from an initial singularity, a point of infinite density, infinite temperature, and zero volume. It's the moment when all the equations break down. According to classical general relativity, as we rewind time, the universe gets smaller and smaller, denser and denser, until crunch, we hit that singularity, a place where space and time cease to be well-defined. But physicists don't like infinities. They're usually a sign that something has gone wrong with the math, like dividing by zero on a calculator and watching it give up. And singularities, as elegant as they sound, are mathematical monsters. They tell us that our theories are incomplete. This is a point of great academic debate. While the Big Bang model explains so much, the singularity at its heart is a puzzle that remains. This is where quantum gravity enters the scene. The search for a theory that unifies the smooth geometry of general relativity with the jittery unpredictability of quantum mechanics. And one of the leading candidates in that search is loop quantum gravity. Loop quantum gravity, or LQG, reimagines space and time not as continuous flowing things, like an infinitely smooth sheet, but as woven granular quantized structures at the smallest possible scales, the so-called Planck scale. Space itself may be made of tiny loops like an intricate mesh or fabric. These loops aren't made of matter or energy, but of the very structure of space. They're the threads from which the cosmic quilt is sewn. Now, when loop quantum gravity is applied to the entire universe, a discipline known as loop quantum cosmology, something remarkable happens. Instead of the universe shrinking into an infinite density singularity as we rewind time, the theory suggests that quantum effects become dominant near that extreme point. These effects generate a kind of quantum pressure that resists further collapse. It's a bit like a trampoline that stretches under weight, but eventually pushes back. The result? Instead of a big bang, we get a big bounce. In this model, the universe didn't begin at a singularity. It began at a bounce point, a minimum size and maximum density, where quantum geometry repelled the collapse. Before that, a contracting universe, a cosmos that had been shrinking, cooling, perhaps even forming stars and galaxies, before reaching the bounce and beginning to expand again, becoming our universe. It's a beautiful reversal. Instead of time having a hard beginning, it becomes a cycle. The bounce replaces the bang. The singularity becomes a bridge. This idea has several appealing features. First, it removes the need for infinite quantities, always a welcome relief in physics. Second, it offers a possible solution to the puzzle of what happened before the Big Bang. And third, it opens the door to an even more profound possibility, that the universe has no beginning at all. In a bouncing model, there may have been many cycles, expansions, followed by contractions, each one giving rise to a new phase of cosmic history. Each bounce wiping the slate clean, or perhaps leaving behind faint traces, subtle fingerprints in the structure of space and time. A historical note here: the idea of a cyclic universe is far from new. It appeared in ancient Eastern philosophies such as Hinduism and Buddhism. Long before modern physics, these traditions described a cosmos that goes through vast repetitive cycles of creation and destruction, much like the Big Bounce model suggests. This parallel between ancient philosophy and modern science is a beautiful thing to ponder. It's as if humanity has been trying to tell itself this story for a very long time. But is there any evidence for this? That's the big question. And scientists are beginning to look. One possible clue lies in the cosmic microwave background, the afterglow of the early universe. If a bounce really happened, and if some quantum features of the previous universe survived the transition, they might leave small imprints, tiny anomalies in the temperature fluctuations, or a particular pattern in the polarization of the light. So far, observations from telescopes like Planck haven't found anything conclusive, but the search continues, and future missions may have the sensitivity needed to test these predictions. A little-known fact is that some researchers are trying to determine if our universe might have memory of a prior universe. This memory could be encoded in subtle ways like a cosmic echo. They are searching for these echoes, a very long, very faint cosmic whisper. Another interesting possibility is that bouncing cosmologies could help explain the smoothness and flatness of the universe without needing inflation. In the standard model, inflation is invoked to stretch out any irregularities. But in some bouncing models, the contraction phase could naturally smooth and flatten. Space making inflation unnecessary, or at least secondary. The ongoing academic debate is a fun one. Is inflation right? Is the big bounce right? Or is some combination of them both true? A fun little joke to lighten the mood. What do you call a universe that keeps bouncing, a cosmic yo-yo? A simple joke for a very complex idea. So what about the deeper philosophical implications? Well, if the big bounce is real, it means that something came before our universe, quite literally. Not a void, not a timeless potential, but a previous cosmos. Maybe it was similar to ours, maybe not. It might have had different physical constants, a different distribution of matter, or even a completely different arrow of time. And if the bounce happens repeatedly, it challenges our sense of cosmic uniqueness. We may be just one era in a long chain of universal epochs, each one rising, evolving, and collapsing in its own time. No first cause, no singular creation, just an eternal heartbeat. This also has implications for the idea of entropy, the tendency of systems to become more disordered over time. In a cyclic universe, entropy would build up with each cycle, making each new bounce more chaotic than the last. But some bouncing models suggest mechanisms to reset entropy or to dilute it during contraction, allowing the cycle to continue indefinitely. Still, many questions remain. What triggers the bounce? How does quantum gravity operate at these extreme scales? Can we test the predictions? Can we ever see past the bounce loop? Quantum cosmology is still a young field, and much remains speculative, but it offers a compelling alternative to the traditional narrative, one that removes the singularity, preserves time before the Big Bang, and hints at a much richer history than we ever imagined. It also softens the mystery of nothing. In this view, there never was nothing. There was always something, a previous universe, or perhaps many leading to the one we see today. No need to explain the emergence of everything from an absolute void, just a continuation, a rebound, a cycle, and it's oddly comforting, isn't it? The idea that our universe is part of a longer story. That time didn't start with us. That before our beginning, there was an end, and before that end, another beginning. A quiet rhythm, a cosmic breath. Inhale, expand, exhale, contract, and again. And again. So the next time someone asks what came before the Big Bang, you can smile softly and say, maybe a bounce. And maybe, just maybe, the universe has been bouncing all along. We've explored the idea of a universe that simply bounced into being a cosmic continuation, rather than a hard start. Now let's take another gentle step forward. Or perhaps it's a step sideways into a truly strange and beautiful possibility. A possibility that doesn't require a pre-existing universe to rebound from, but instead suggests that reality itself could have arisen from a state of pure, unadulterated nothingness. This might sound like a bedtime fairy tale. Once upon a time, there was no time. But in the curious world of theoretical physics, it's a serious attempt to understand how everything could have emerged from what we once called nothing. Tonight, we're going to float gently into one of the boldest ideas in modern cosmology, the notion that the universe could have quantum-tunneled into existence. A model proposed by physicist Alexander Vilenkin and others, where reality itself flickered into being, not from a divine command or a fiery explosion, but from a quiet quantum possibility. Now, before we tiptoe into tunneling, let's revisit something we learned in an earlier chapter. The vacuum is never truly empty. Even the calmest space bubbles with quantum fluctuations, little borrowings of energy that vanish as quickly as they appear. This is because of the strange logic of the quantum world, where things that are forbidden in classical physics can still happen as long as they don't last too long. And this idea that nature has some flexibility, a kind of quantum wiggle room, brings us to quantum tunneling. In classical physics, if you throw a ball at a wall and it doesn't have enough energy to get over the top, it will just bounce back. That's it. Game over. But in quantum physics, there's a chance, a small but real one, that the ball could simply appear on the other side of the wall. Not because it jumped over or tunneled through in the usual sense, but because particles aren't like tiny marbles. They're like waves, fuzzy, probabilistic, slightly mischievous waves. And sometimes, those waves allow things to appear where they shouldn't be allowed according to our everyday expectations. This phenomenon is not just a theory. It's been observed in countless experiments. It's how nuclear fusion happens in stars. It's how some particles decay, and it might just be how the universe was born. So how does that work? let's ease into Alexander Vilenkin's idea, one of the most quietly radical ideas in all of cosmology. A historical fact that is often overlooked is that Vilenkin's work built upon the foundation laid by physicists who were exploring the idea of a universe with no beginning, particularly the no-boundary proposal of Hawking and Hartley. But Vilenkin's approach was different. Instead of a universe rounding off a beginning, his model suggested a spontaneous, probabilistic event. In the early 1980s, Vilenkin proposed that the universe could have tunneled into existence from a state with no classical space, no time, and no matter. In other words, from nothing. But this wasn't an ordinary nothing. It wasn't empty space. It wasn't a vacuum waiting to be filled. It was the absence of all physical structure, yet somehow still governed by the rules of quantum physics. This sounds strange, and it is. But remember, quantum physics allows for possibilities that defy classical intuition. In Vilenkin's model, the universe didn't need a cause in the traditional sense. There was no ticking clock before it, no spatial coordinates to mark its arrival. Instead, it was like a particle appearing on the other side of an impossibly high wall. Not because it climbed over, but because the laws of quantum mechanics gave it a tiny but non-zero chance to exist there. This is sometimes called quantum cosmogenesis, the birth of a cosmos through quantum means. And it comes with a remarkable feature. The probability of tunneling is related to the energy of the resulting universe. That is, smaller, simpler universes are more likely to tunnel into existence than larger or more complicated ones. But our universe is so vast. Well, this is where inflation comes in. A little-known detail is that Vilenkin's tunneling model naturally leads to a universe that begins in a state of rapid inflation. The tunneling event itself could have triggered the inflaton field we discussed, which then swelled the universe to its immense size. Now, if you're wondering, wait, how can quantum laws exist in a place with no space or time? You're not alone. It's a delicate philosophical and scientific question. Some physicists argue that quantum laws are so fundamental, they don't need a pre-existing universe to operate. They're not like traffic rules written on signs. They're more like the blueprint of possibility itself. You can think of it like this. Even if there is no game board yet, the rules of chess still exist conceptually. And once the board appears, those rules dictate how pieces can move. Similarly, the pre-universe nothing in Vilenkin's model doesn't have a game board, no space-time, no geometry, but it may still be shaped by quantum rules that determine what can happen and how likely it is to happen. An open academic question is whether these laws themselves are eternal, or if they too emerged in some way. It is a mystery wrapped in a mystery, which can be either terrifying or, if you're feeling sleepy, incredibly peaceful. And according to this idea, what can happen is astonishing. An entire universe complete with its own space-time energy and physical laws can tunnel into being, and we might be living in it. So where does this leave us in our journey to understand nothing? Well, it shifts the question a bit. In Vilenkin's model, there may be no before the universe in the traditional sense, but there is a mathematical space of possibility described by quantum laws. The nothingness isn't an empty box. It's more like a potential, a kind of seedbed of realities that could bloom. Given the right moment, or perhaps more accurately given the right absence of moment. Since time itself doesn't yet exist in this state, this idea of the universe as a spontaneous probabilistic event might feel strange or even a little unsatisfying. We're used to thinking of causes. Things happen because of something else. But in the quantum world, some events don't need causes in the usual sense. They're allowed to happen by the rules of probability, not by the rules of determinism. And what's especially lovely about Vilenkin's model is that it doesn't require any exotic ingredients. No mysterious pre-existing space, no divine spark, just quantum mechanics doing what it always does, allowing unlikely things to happen given enough time, or in this case, giving birth to time itself. A little joke to ease the mind. What did the universe say to the quantum fluctuation that created it? Hey, thanks for just, being there. Of course, this is still speculative. No one has a telescope powerful enough to peer before the Big Bang or into the quantum fuzz that may have preceded it. These are ideas grounded in mathematics and theory, not direct observation, but they offer a tantalizing glimpse at how the universe might have emerged, not in a bang, but in a whisper of possibility becoming reality. And here's a little bonus twist. Because quantum mechanics is symmetric in time, there are models where the universe doesn't just tunnel forward into existence, it might tunnel symmetrically with two time directions emerging from the same starting point. That is, there could be a mirror universe expanding in the opposite direction in time from ours. Don't worry, you won't meet your backward self at the grocery store. But it's another example of how strange, elegant, and mysterious the quantum origin of the universe might be. So, could quantum tunneling from nothing be the answer to how everything began? Possibly. It's one of the best guesses we have, and it's a gentle, profound idea that the entire cosmos may have started as a tiny chance event born from a rulebook that doesn't need a referee or even a field to play on. It's humbling, it's mind-bending, and it's strangely soothing. From nothing, or almost nothing, came everything. Not with a bang, but with a quantum shrug. Let's take a curious detour now. One that's less about a singular moment and more about an eternal process. We're going to float calmly through the vast and mysterious idea that our universe, with all its galaxies and glittering stars, is just one tiny bubble in an endless cosmic foam. One pocket of space among countless others, each with its own laws, histories, and possibilities. It's a humbling, almost dizzying idea. But according to a theory known as eternal inflation, this may be exactly what reality looks like on the grandest of scales. This is a universe of universes, a multiverse born not from a singular explosion, but from a quiet, endless process of cosmic bubbling. A process that, if true, would mean that the idea of nothing may never have existed at all. To begin, let's return briefly to the theory of cosmic inflation, which we visited a few chapters ago. Inflation proposes that the early universe underwent an incredibly rapid expansion, driven by the energy of a special field, the inflaton. This expansion smoothed out space, solved several cosmological puzzles, and set the stage for the hot Big Bang that followed. In the simplest versions of the theory, inflation is like turning on a fire hose. It blasts out a universe-sized patch of space, then turns off, and the universe evolves from there. But in the more nuanced and frankly more intriguing versions of the theory, inflation doesn't stop everywhere. In fact, it can't, because quantum fields are not perfectly smooth or predictable. There are tiny fluctuations in the inflaton field from place to place. In some regions, the field might drop in energy and inflation ends. That's where a universe like ours begins. But in other regions, the field might remain high and inflation continues. Those regions expand faster and faster, outpacing the regions where inflation ended. And while universes like ours stop inflating and cool into stars and galaxies, the space between them keeps growing. This leads to a self-replicating runaway process, eternal inflation. Think of it like boiling water in a pot. As it heats, little bubbles form and rise to the surface. But imagine that instead of the bubbles popping and disappearing, they became their own separate worlds. Now imagine that the boiling never stops. More and more bubbles form endlessly, each one expanding and evolving in its own way. That's the multiverse as imagined by eternal inflation. A little-known fact about this theory is that it was a surprising consequence of inflation models, not something physicists were originally looking for. It emerged naturally from the math, which is often a sign that an idea has a beautiful internal logic. The ongoing academic debate is a lively one. Is eternal inflation a prediction, or is it just a theoretical consequence that can't be proven? Each bubble in this cosmic stew represents a universe. Some might be similar to ours. Others might have different physical laws, different particles, different forces, perhaps even different numbers of dimensions. In one bubble, gravity might be weaker. In another star's, might never form. In yet another space, might curve back in on itself like a sphere. The variety could be endless. A little joke to ease the mind: what's the most common greeting in the multiverse? Hey, which reality are you from? It's a nice thought, isn't it? And here's the truly staggering part. This bubbling isn't just vast, it's eternal. Because in the regions where inflation doesn't stop, space keeps expanding exponentially. The faster it expands, the more room it creates for new bubbles to form. These bubbles are isolated from each other, separated by ever-growing expanses of inflating space. They can't interact. They might never even know about one another. But together, they form what's sometimes called the inflationary multiverse, an infinite landscape of universes, born not from nothing, but from a process that never stops. So what does this mean for the idea of nothing? Well, it may suggest that nothing true, absolute, total. Nothing never existed. There was never a blank slate, a moment of perfect stillness before something emerged. Instead, there's always been something happening somewhere, a bubbling, stretching, inflating cosmos, branching out forever. In this picture, our universe didn't arise from a singular beginning. It was just one of countless nucleation events where a region of space exited inflation and began evolving in the way we're familiar with. That means the Big Bang as we know it wasn't the beginning, just our beginning. A historical note here is that the multiverse concept has been quietly present in philosophical thought for centuries, if not millennia. Ancient Greek atomists, for instance, envisioned an infinite number of worlds forming from countless atoms in a vast void. The idea has always been an elegant solution to the problem of a unique, singular creation. It's a way to explain the universe without resorting to a single, inexplicable event. Of course, this might sound like science fiction, or at the very least wildly speculative, and to some extent, it is speculative. We don't have direct evidence of other bubbles. We can't peer into other universes to confirm their existence. But eternal inflation isn't just a fantasy someone scribbled onto a whiteboard. It's a natural mathematical consequence of certain inflation models that fit very well with what we do observe, especially in the cosmic microwave background. It also ties in with other branches of theoretical physics. For example, in string theory, a framework that attempts to unify all the fundamental forces. There isn't just one solution for the shape of reality. There may be a landscape of possible configurations, each with its own unique set of laws. Eternal inflation could be the engine that explores that landscape, bubbling off new universes to try out each possibility. Some physicists even argue that this helps explain something very strange about our universe, why its physical constants seem so finely tuned for life. Gravity, electromagnetism. The masses of particles, if any of them were just slightly different complex matter, might never form. Planets might not exist. Chemistry wouldn't work. No stars, no life, no sleepy science videos. But if there are countless universes, each with slightly different properties, then it's not so surprising that at least one ours happens to have just the right ingredients. It's not that we're lucky. It's that we're in the one place where observers can exist to ask the question. This idea is sometimes called the anthropic principle. It doesn't mean we're special, just that our presence tells us something about the kind of bubble we happen to live in. A final gentle joke for the road. What did the universe say when it met the anthropic principle? You can't prove anything, but I sure am glad you're here to ask. Now, understandably, not everyone loves this idea. Some scientists find the multiverse unsatisfying because it seems hard to test. If we can never observe the other bubbles, can we really call this science? Is it philosophy wrapped in math? That's a fair criticism, and one the scientific community continues to debate. But there are efforts to find indirect clues. For example, some theories suggest that if two bubble universes ever bumped into each other like soap bubbles in a sink, the collision might leave a mark in the cosmic microwave background. We haven't seen such a mark yet, but researchers are looking. Others explore whether gravitational waves, ripples in spacetime, might carry information from such collisions. Since gravitational waves interact very weakly with matter, they could preserve ancient information that other signals cannot. Perhaps someday we'll hear the faint echo of bubbles colliding, a whisper from the higher dimensions. Until then, eternal inflation remains a beautiful, compelling, and speculative extension of our best cosmological models. So where does this leave us? It leaves us with a new way of thinking about everything. Not as a singular event in a pre-existing void, but as one chapter in a never-ending story. A story that's been unfolding forever, not in time as we know it, but in the boundless potential of space itself. In this view, nothing becomes a kind of illusion. There is always something afield, a fluctuation, a slow, eternal bubbling. It's a quiet, expansive idea that the cosmos has no beginning and no end. Just an endless generation of possibilities branching and inflating, like foam in a never-emptied kettle. And somewhere in all that infinite froth, there's us. One bubble with just the right balance. One flicker of light in an endless ocean of possibility. And that, too, is something. Let's take a gentle step into a more abstract realm now, a place where the fabric of reality is not woven from particles and fields, but from tiny vibrating strings. A place where dimensions aren't limited to up, down, left, right, and time, but stretch far beyond our senses. It's a place where the universe, as vast as it seems, might be just one membrane floating in a much larger cosmic sea. Welcome to the strange and beautiful world of string theory and its even stranger cousin, brain cosmology. Now don't worry if this all sounds like science fiction at first. String theory does have that vibe. It's bold, mathematically rich, and still very much a work in progress, but it's also one of the most serious attempts physicists have made to unify the fundamental forces of nature to understand the smallest building blocks of matter, while also describing how the universe itself came to be. Let's start softly with the basics. In traditional physics, the kind you might encounter in everyday conversations about atoms and molecules, we think of particles as tiny points, electrons, quarks, neutrinos. They're considered to be zero-dimensional dots with no size, just mass and charge. But in string theory, those particles are not points at all. They are tiny one-dimensional strings. Each one is unimaginably small, about 100 billion times smaller than a proton. These strings vibrate at different frequencies, and the way they vibrate determines what kind of particle they represent. A low-frequency vibration might give you an electron. A higher one might give you a photon. It's a little like musical notes on a violin string. Different tones for different patterns. This elegant framework allows for the unification of forces that were previously hard to reconcile. Gravity, for instance, plays very poorly with quantum mechanics in the traditional model. But in string theory, gravity appears naturally as a particular vibration of a string 1 that corresponds to a hypothetical particle called the graviton. But to make all this math work out, string theory requires something unexpected: extra dimensions. Not just the 4 we're used to, length, width, height, and time, but up to 10 spatial dimensions, or even more depending on the version of the theory. Now you might be thinking, where are these extra dimensions? I don't see them when I'm brushing my teeth or looking at the sky. According to string theory, these extra dimensions are compactified, curled up so tightly that they're imperceptible to us. Imagine a garden hose from far away. It looks like a one-dimensional line, but get up close and you see it has a circular shape. The idea is that the extra dimensions are like the circular shape of the hose, present but hidden at very small scales. A historical note here: the idea of hidden extra dimensions actually dates back to the early 20th century with the work of Theodore Kaluza and Oscar Klein, who attempted to unify electromagnetism and gravity using a 5th dimension. They were working with a very simple, elegant idea: But string theory took it to a whole new, much more complex level. So what does all this have to do with the origin of the universe? This is where things get truly fascinating, and where brain cosmology enters the picture. In some versions of string theory, particularly M theory, which is like a big umbrella theory that unifies all the others. Not only do strings exist, but so do higher dimensional objects, called brains, short for membranes. These can be two-dimensional surfaces, three-dimensional volumes, or even higher. Our universe, according to some models, might actually be a three-dimensional brain, a kind of membrane floating in a higher dimensional space. Imagine a vast ocean with sheets of paper drifting through it. Each sheet is a brain. A universe is one of those sheets. We're stuck to it like ants walking on a piece of paper. We can move left, right, up, down, forward in time, but we can't step off the page. Now here's where things get exciting. In brain cosmology, it's possible that there are other brains floating nearby parallel universes, if you will. And sometimes these brains can collide. One of the leading ideas in this area is called the ekpyrotic model, a word borrowed from ancient Greek, meaning conflagration or fire. In this model, our universe wasn't born from a singular explosion or a random fluctuation. Instead, it was born from the collision of two brains in a higher dimensional space. When these brains crash into each other, they release an enormous amount of energy, enough to heat the universe and create the conditions we associate with the Big Bang. But unlike the traditional Big Bang model, this version doesn't start from a singularity. It starts from a geometric higher dimensional event, a kind of cosmic fender bender. And it doesn't have to happen only once. In some brain models, this collision and the expansion that follows is cyclical. The brains pull apart after the collision, then are drawn back together again by gravity, leading to another collision, another Big Bang, and another cycle of cosmic history. It's not a one-time beginning, but an eternal dance of dimensions. This model shares something in common with the Big Bounce idea we explored earlier, the concept that the universe goes through cycles of contraction and expansion. But in brain cosmology, the bounce isn't just a quantum rebound. It's a collision in a higher dimensional space. A little-known fact is that this theory was originally developed to offer an alternative to the inflationary model, providing a different solution to the horizon and flatness problems. It suggests that the flatness of our universe is a natural consequence of the geometry of the brains, not an exponential stretch. This creates a lively academic debate between proponents of inflation and proponents of brain cosmology. Which one is right? Or are they both incomplete parts of a larger picture? A joke that's only funny if you're a string theorist. Why did the electron break up with the proton? Because it was tired of him being so point-like, and she wanted a one-dimensional relationship. And what about nothing? In this framework, nothing in the absolute no space, no time, no laws sense may never have existed. Instead, there may have always been a higher dimensional space, with brains moving through it. Our universe's beginning wasn't the emergence of everything from nothing, but the transformation of energy from one form to another, the sudden release of potential trapped between colliding sheets. This is the beauty of it, isn't it? The universe's origin is simply a transformation, not a creation from scratch. It is a new chapter in a story that was already unfolding. Of course, all of this is speculative. As elegant as these ideas are, we don't yet have direct evidence for extra dimensions, strings, or brains. The math is intricate and beautiful, but the experimental confirmation remains elusive. Still, there are potential observational clues. For instance, collisions between brains could leave imprints in the cosmic microwave background, subtle signatures in the temperature patterns of the ancient light. Some researchers are looking for these signals, hoping to distinguish brain collisions from other early universe events. Others are exploring whether gravitational waves' ripples in space-time might carry information from such collisions. Since gravitational waves interact very weakly with matter, they could preserve ancient information that other signals cannot. The ongoing academic debate is still very much open, as to which model, if any, is truly correct. Perhaps someday we'll hear the faint echo of brains colliding, a whisper from the higher dimensions. Until then, brain cosmology remains a profound possibility that our universe is just one piece of a much larger structure. That reality includes hidden dimensions, invisible spaces and universes stacked like pages in a cosmic book. And maybe, just maybe, our Big Bang wasn't the beginning. Maybe it was the sound not of a bang, but of two brains brushing past one another like silk sheets in a darkened room. So as you drift off tonight, let your thoughts wander across dimensions. Picture the universe not as a singular moment, but as part of a graceful unseen dance, a choreography of brains, strings, and gentle collisions in a space beyond our own. In that vast quiet, the music of creation still plays. And you, a little creature made of vibrations on a membrane, are a part of that beautiful, endless song. We've traveled through quantum fields, imagined cosmic bounces, and floated on vast cosmic brains. We've used the instruments of science equations, telescopes, and thought experiments to probe the nature of nothing. But now, let's take a quiet meander away from the sharp edges of physics and into the soft, flickering candlelight of philosophy. For while equations and models help us understand how the universe may have begun, it is philosophy that asks the deeper, more unsettling question: why anything at all? What does it mean to speak of nothing? What, if anything, could it ever be? The notion of nothing has haunted human thought for millennia. It lingers behind every question we ask about beginnings, endings, and what lies between. And though it may seem like a simple concept, the absence of everything philosophers have shown time and again that nothing is anything but simple. Our journey begins, as it often does, in ancient Greece. The earliest thinkers in the Western tradition were not afraid to wrestle with big ideas. They stood on the edges of myth and reason, looking out at a world newly stripped of its gods, and tried to understand what was left behind. And one of the earliest and most stubborn of these thinkers was Parmenides, a philosopher from the city of Elea, writing around the 5th century BCE. Parmenides is often remembered for saying something that seems at once obvious and completely baffling: nothing cannot be. In other words, non-being, true nothingness is impossible. According to Parmenides, we can't even think about nothing, because the very act of thinking presupposes that there's something to think about. To speak of what is not is to fall into a contradiction. For him, only being exists, eternal, unchanging, and whole. This might sound like a philosophical tongue twister, but Parmenides was making a profound claim. He believed that change, motion, birth, and death were illusions, that reality was a single, unchanging entity, and that all appearances of difference and absence were tricks played by our limited senses. Nothing wasn't just unthinkable, it was impossible. As you might imagine, not everyone agreed. His philosophical adversary, or perhaps his cosmic counterweight, was Heraclitus, who lived around the same time. Heraclitus saw the world not as static, but as a river of constant change. You cannot step into the same river twice, he said, because everything is always in flux. Where Parmenides saw permanence, Heraclitus saw fire. Heraclitus didn't focus on nothing directly, but his vision of a world built from opposites, light and dark, life and death, fullness and emptiness, made room for absence. For him, what is cannot be understood without also knowing what is not. A historical fact is that the tension between Parmenides' view of a static reality and Heraclitus' view of a dynamic one has echoed throughout the entire history of Western philosophy. From Plato and Aristotle all the way to modern physics, it's an academic debate that has never truly been resolved. Fast forward a few centuries to the more practical thinkers of Athens, and we find Democritus and the atomists, who gave us the first known theory of the vacuum. To them, the universe was made of indivisible particles, atoms moving through empty space. They needed nothing. Quite literally. In their theory, a void in which matter could move, combine, and create the world. This was a daring move for the atomists. Nothingness was not a contradiction. It was a background, a necessary absence, an emptiness without which nothing could ever happen. This was a little-known detail in the grand history of thought. For a long time, the atomists' ideas were considered radical and even heretical by many, especially those who followed Aristotle. Plato, however, wasn't so sure. He distrusted the senses and the notion of a physical void. In his view, the world of appearances was a pale imitation of eternal forms, perfect immaterial patterns. To Plato, the absence of form wasn't meaningful. The real was what was eternal. Nothingness, like shadows on the cave wall, didn't deserve much attention. But it was Aristotle, Plato's student, who really grappled with the concept. He rejected the idea of a vacuum, believing that nature abhors a vacuum, and that every region of the cosmos must be filled with something ether air, or some kind of substance. He didn't believe in nothingness, because to him everything that exists does so in something. Space in his mind had to be full, and for more than 1,000 years, this view held sway. Through the Middle Ages and the rise of scholastic philosophy, Aristotle's teaching shaped much of how Europe thought about space-time and the void. Nothing was not real. It was an absence, yes, but not a thing in itself. Then came the scientific revolution, and with it, a slow but steady shift in our understanding. Thinkers like Galileo, Descartes, and Newton began to explore space not as a filled container, but as a geometric stage. Newton's universe especially required empty space, a backdrop of absolute space and time where forces acted across great distances. Descartes, on the other hand, was uncomfortable with such voids. He famously said, "I think, therefore, I am grounding existence in thought itself." But for Descartes, extension, the property of taking up space, was inseparable from matter. If there was space, then there had to be something in it. Still, the idea of the vacuum was gaining ground. By the time of Pascal and Torricelli, experiments showed that air had weight and that you could, in fact, create vacuums. Nothingness, at least in the physical sense, seemed to be real, or at least experimentally useful. It was a funny moment in history when the vacuum was proven to exist. A joke in the philosophical community went something like this: Torricelli proved the vacuum exists. Now all the Aristotelians have nothing to stand on. But the deeper question, what is absolute nothing, continued to haunt philosophy. Enter Martin Heidegger, a 20th century German philosopher who brought the question back to the center. In a lecture titled, "What is Metaphysics?" Heidegger asked perhaps the most unsettling question of all. Why is there something rather than nothing? It sounds simple, but sit with it for a moment. Really sit with it. Why is there something? Why is there anything, a universe, a mind, a single heartbeat, instead of the pure stillness of non-being? Heidegger saw this as the ultimate question. He believed that we're usually so busy being existing, doing living, that we overlook the mystery of being itself. And behind that mystery is the void. Not a physical vacuum, but an existential absence, the possibility that nothing could have been. And yet, here we are. Heidegger's approach wasn't analytical. It was more poetic, more meditative. He urged us to stand before nothing, not to explain it away, but to experience its strangeness. The void, he said, reveals the fragility and wonder of being. It makes us aware that existence is not a given, that it could have been otherwise, that it could have been not at all. And perhaps that is the most profound insight philosophy offers us about nothing. That it is not a mere placeholder or a background or a technical term. It is a question, a haunting presence, a kind of silence that echoes behind every thought, every breath, every star. When science asks what caused the Big Bang, philosophy whispers, why anything at all? When physics models a vacuum, philosophy asks what it means for that vacuum to be. When cosmology builds universes from fields and equations, Philosophy wonders if all of that is just a bright flicker in an eternal darkness. An ongoing academic debate that will likely never be resolved is the relationship between this philosophical nothing and the scientific nothing. Are they the same thing? Or are they two distinct ideas? One a matter of language and perception, the other a matter of physics and potential. And while we may never answer those questions fully, perhaps that's not the point. Perhaps like the Greeks sitting under olive trees, or the existentialists staring into the night sky, our task is not to solve the riddle of nothing, but to dwell in it, to feel its chill, to respect its presence. Because in that space, that void, we glimpse the fragility of our own being and the wonder that anything at all exists. A soft question murmured across millennia. What is nothing? And the equally soft reply, you are something. And that perhaps is enough. And now here we are at the quiet end of our long journey. We've drifted through fields of quantum foam, swam gently through multiverses, tiptoed across the rounded edge of time, and even wandered down the rabbit holes of philosophy and simulated realities. We've asked whether nothing ever truly existed. We've examined models, theories, and ancient ideas that have tried to draw a line between nothing and something, between silence and song, between absence and being. And now gently, we arrive at a place not of resolution, but of rest. Because after everything, after bouncing universes, imaginary time vibrating strings, and virtual hard drives, we're left with something unexpectedly soft. The possibility that not knowing might be the most honest and the most beautiful place to end up. In the beginning of this journey, we asked simple but profound questions. Did nothing ever exist? Could there have been a time before time, a space before space, a place where nothing real, total, absolute, nothing was all there was? And we asked, what does nothing even mean? Is it a blankness we can picture, or a concept that slips through our fingers the moment we try to hold it? Now, after 9 chapters of slow, thoughtful exploration, the answers may still feel just out of reach, not because we missed them, but because the questions themselves were never about arriving at a finish line. They were an invitation, a widening of perspective, a way to look at the universe and ourselves within it with a little more wonder. Maybe nothingness never existed. Maybe the universe has always been. Maybe reality has no edge, no first moment, no switch that flipped. Maybe the laws of physics, or something even more subtle, have simply always been at work humming quietly through infinite time. Or maybe nothing really did come before everything. Maybe there was a true void, not the vacuum of space, not a quiet room without matter, but the deep, unimaginable absence of anything at all. And from that, nothing something arose, a flicker, a ripple, a question, a bang, a breath. We might never know which is true. And strangely enough, that might be the point. There's a quiet kind of courage in being able to sit with mystery, to let questions remain open, to admit that the universe, in all its magnificence, may not yield every answer. Not because it's hiding them from us, but because some answers may not fit within the language of questions. Some mysteries may be woven into the fabric of existence, not to frustrate us, but to deepen our sense of wonder. Because uncertainty, when approached gently, is not frightening. It's freeing. Think of the sky on a cloudless night, all that space, all that starlight, all that silence. The universe doesn't rush to explain itself. It simply is, and it allows us little thoughtful beings, clinging to a speck of rock, to look up, to wonder, to ask. And asking in itself is beautiful. Even if we never find out whether nothing came before the cosmos, even if we'd never peer past the Big Bang or decode the source code of reality, the act of wondering shapes us. It keeps our minds open and our imaginations wide. It connects us not just to science or philosophy, but to the whole human experience, the part of us that sits quietly and simply wants to understand. The mystery of nothingness is not a flaw in the universe. It's a feature, a space left open, like a pause in a piece of music, a place for us to rest, to breathe, to marvel. And the fact that we don't know that we can't know does not make us small. It makes us part of something far greater than we could ever fully grasp. So wherever the universe came from, whether it tunneled out of a quantum vacuum, rebounded from a previous cosmos, or emerged from nothing at all, here we are. Alive, aware, able to ask. And maybe that's enough to be a creature capable of wondering what existed before anything else. That alone is a miracle. A star becoming conscious of stars, a ripple in space-time asking what made the water stir. So why does any of this matter? What does it change to wonder what came before the universe? Or if there was ever truly a nothing at all? We still live our lives. We still make coffee, fold laundry, answer messages, and yawn. Whether the universe began with a bang, a bounce, a fluctuation, or a line of code, the cat still expects to be fed in the morning. So why do we keep coming back to these questions? Why do we care so much about what came before? Maybe the answer is woven into what it means to be human. Not just curious, but insatiably curious. We're a species that stares at campfires and wonders how far back we can trace the flame. We build myths and telescopes. We look up and inward. And when we run out of answers, we sit in the questions anyway. At first glance, it might seem like knowing what came before the Big Bang wouldn't make a difference to your day-to-day life. And in a strictly practical sense, that might be true. It won't help you remember where you left your keys. It won't file your taxes or fold your laundry. But that doesn't mean it's irrelevant. Not even close. Because asking where the universe came from, what it's made of, whether it had a beginning, whether nothing ever truly existed, isn't really about solving a problem. It's about understanding where we stand. It's about stepping back far enough that we can see not just the picture, but the frame. You, me, everyone we know. We are made of the universe, literally. Our bodies are built from atoms forged in ancient stars. Our thoughts are electric pulses shaped by the same laws that guide galaxies. When we ask what came before everything, we're really asking something much deeper. What are we in the grand story of existence? Even if the answers never arrive, the act of asking shifts our perspective. It pulls us out of the small loops we get caught in, the minor worries and the habitual routines. It reminds us that we are temporary passengers on a very old train, hurtling through something vast and beautiful and strange. And that shift in perspective can ripple through your life in quiet but powerful ways. When you remember that the universe might be infinite, that time itself might not have had a beginning. That even nothing is more complicated than it seems, you begin to see everything else a little differently too. A traffic jam might feel a little less frustrating. A quiet walk might feel a little more profound. Even the familiar rhythm of your own breath can become a kind of miracle. Because here's the thing, you didn't have to exist, and yet you do. Not just as a biological fluke or a lucky arrangement of particles, but as a conscious being capable of wondering, capable of holding in your mind not just your own past, but the possible past of everything. That's extraordinary, and it's part of why these questions are worth asking. They're not distractions from real life. They are real life at its most wide awake. There's also something deeply comforting in zooming out this far and recognizing that the universe has been around for billions of years and may continue for billions more. That the problems we carry, while real and weighty, are often small ripples in a much vast sea. The deadlines, the to-do lists, the occasional existential panic about whether you're doing life right. All of it is framed by the immense backdrop of a universe that doesn't judge, doesn't rush, and doesn't demand that we solve everything. The universe asks nothing of us, and yet we ask everything of it. We ask why we're here, why anything is here, why there's something rather than nothing. And through those questions, we come into contact with our own fragility and our own wonder. It's also worth noting that these questions aren't just the territory of physicists and philosophers. They belong to all of us. You don't need a PhD to feel awe. You don't need equations to ask what existed before the beginning. All you need is a quiet moment, a curious mind, and maybe the willingness to sit with a little uncertainty. And perhaps that's the most important part, the uncertainty, the not knowing. There's a kind of peace in admitting that we might never fully understand what preceded the universe, or whether that question even makes sense. There's humility in recognizing the limits of what we can know, and in that humility, a surprising kind of freedom. Because once you let go of needing a perfect answer, you can fall in love with the question itself. You can explore, imagine, wonder, and dream, not to arrive at a final truth, but to expand your sense of what's possible. And that expansion is a kind of growth, a kind of awakening. A little-known fact from the history of science is that many of the greatest scientific breakthroughs came from people who were willing to embrace uncertainty. They saw something that didn't fit with the current understanding, and instead of dismissing it, they sat with the puzzle. They lived in the question. And that is what we are doing now. It's a very human thing to do, as we've seen. The academic debate over the nature of nothing has raged for thousands of years, and it's a testament to our enduring curiosity. A final gentle joke for our journey. What did one particle say to the other as they popped into existence from the quantum vacuum? I'm not sure where we came from, but it sure is good to be here. The universe, in its grand silence, seems to be okay with not having a clear start. It just is. And in that grand gesture of simply existing, it gives us permission to be here, to be okay with our own beginnings, and to find peace in the unanswered questions of our own lives. We often think of science and philosophy as cold or abstract, but they're not. At their best, they're acts of love, acts of reverence for the mystery of being. Every equation ever written, every thought experiment ever proposed is a human reaching out into the dark, whispering, "Tell me more." And whether or not the universe whispers back, the reaching is meaningful. So why does it matter what came before the universe? It matters because it reminds us that we're part of a much bigger story. A story that may have no beginning and no end. A story written in galaxies and quarks and quiet questions. It matters because it shifts our gaze from the mirror to the sky. It matters because asking what is nothing helps us appreciate everything. And it matters because at some deep level, it reminds us we're not separate from the cosmos. We are the cosmos thinking about itself.